December 2022. The James Webb Space Telescope aimed at a patch of sky smaller than a grain of sand held at arm's length. When the data came back, astronomers went silent. Then one of them said the words nobody wanted to hear. This breaks everything we know about the universe. What did they find? Galaxies that shouldn't exist, structures too massive to form, objects that defy the laws of physics as we understand them. And it gets worse. The deeper Webb looks, the more wrong our theories become. Christmas Day, 2021. After decades of delays, billions of dollars, and countless sleepless nights, the James Webb Space Telescope launched into space. It was humanity's most ambitious attempt to see the earliest moments of cosmic history. Webb isn't like Hubble, it doesn't orbit Earth. It sits at a point called L2, about 1 million miles away, where Earth and Sun's gravity balance out. It's essentially alone in deep space, unfurling a tennis court-sized sun shield and a 21-foot golden mirror made of 18 hexagonal segments. Here's what makes Webb special. It sees in infrared. While Hubble captured visible light, the same light your eyes detect, Webb captures heat signatures and redshifted light from objects so distant that the universe's expansion has stretched their light beyond visible wavelengths. This means Webb can see through cosmic dust clouds that block visible light. It can peer into star-forming regions where new solar systems are being born. Most importantly, it can look back in time. Light travels fast, but space is incomprehensibly huge. When you look at the sun, you're seeing it as it was 8 minutes ago, because that's how long light takes to travel 93 million miles. Look at the nearest star system, Alpha Centauri, and you're seeing 4 years into the past. The most distant galaxies Hubble could see existed about 400 million years after the Big Bang. Webb was designed to push past that, to see the very first stars that ignited in the primordial darkness, to witness cosmic dawn. Scientists had theories about what those first galaxies should look like. Small, dim, chaotic, building blocks that would eventually merge into the massive spiral galaxies we see today. Then Webb looked, and everything was wrong. July 2022. NASA released Webb's first deep field image. The photo captured thousands of galaxies, some of the oldest ever observed. Astronomers started analyzing the data, measuring distances, calculating ages. Then the panic started. One galaxy, catalogued as Glass Z13, appeared to exist just 300 million years after the Big Bang. But it wasn't small and dim. It was massive, organized, filled with billions of stars. Another galaxy, Sears 93316, seemed even older, maybe 250 million years post-Big Bang, and it was bright, structured, impossibly mature. Dr. Dan Coe from the Space Telescope Science Institute said what many were thinking. We found something we can't explain with current theories. Here's the problem. Building a galaxy takes time. According to our models, the first stars formed from pure hydrogen and helium because no heavier elements existed yet. These population 3 stars had to live and die, exploding as supernovae, scattering carbon, oxygen, iron across space. Then a second generation of stars formed from this enriched material. Then those stars needed to cluster together, pulled by gravity into proto-galaxies. Then those proto-galaxies merged, grew, developed spiral arms or elliptical shapes. This process should take 1 billion years minimum. Like building a skyscraper, you need time to lay the foundation, construct each floor, install the plumbing. You can't skip steps. But these Webb galaxies are like finding fully furnished penthouses 10 minutes after construction began. It's not just unlikely, it's impossible under our current understanding of physics. Then came JWST Z13-0, another impossibly mature galaxy. Then Sears 1749, then dozens more, each one older than it should be, more massive than it should be, more organized than it should be. By September 2022, astronomers were using words like crisis and paradigm shift. Some even said the Big Bang theory itself might need revision. Professor Mike Boylan-Colchin at the University of Texas ran the numbers. These galaxies contain so many stars that they would have needed to convert nearly 100% of available matter into stars. Not 10%, not 50%. Essentially all of it. That's not how star formation works. It's messy, inefficient. Most gas stays as gas. The star formation rate would need to be 10 times higher than anything we've observed anywhere else in the universe at any time in cosmic history. Either our distance measurements are wrong, our understanding of star formation is wrong, our models of early universe conditions are wrong, or something even stranger is happening. But wait, it gets worse, because it's not just galaxies, it's what's hiding inside them. At the center of most large galaxies sits a supermassive black hole. Our Milky Way has one, Sagittarius A, weighing 4 million times the Sun's mass. These cosmic monsters are surprisingly common, and their size usually correlates with their galaxy's size. Webb found supermassive black holes in these ancient galaxies, black holes weighing billions of solar masses, existing just hundreds of millions of years after the Big Bang. Black holes grow by eating. They pull in gas, dust, sometimes entire stars. But there's a speed limit to this process called the Eddington limit. When matter falls into a black hole, it heats up and radiates energy. This radiation pushes outward, counteracting gravity's inward pull. Push too hard and the black hole stops feeding itself. This means black holes can only grow so fast, no matter how much food is available. It's like trying to drink from a fire hose. There's plenty of water, but you can only gulp so much before physics intervenes. To grow a billion solar mass black hole through normal feeding in 300 million years, you'd need to start with a seed black hole of at least 10,000 solar masses, feeding continuously at maximum efficiency, never stopping. But where does the seed come from? The first stars weren't that massive. They might create black holes of 10 to 100 solar masses when they died. Getting from 100 to 10,000 is another 1,000-fold jump that takes time. Webb found a black hole in galaxy UHZ-1 that's 40 million solar masses, existing 470 million years after the Big Bang. Another in Sears 1019 weighing 9 million solar masses at 570 million years. These numbers don't work. The timeline is too compressed. Some scientists proposed direct collapse black holes, where massive gas clouds collapse straight into black holes without forming stars first. But we've never seen this happen. It's theoretical. Others suggest primordial black holes formed in the Big Bang itself, providing ready-made seeds. But that requires exotic physics we can't test. Dr. Priyamvada Natarajan at Yale studies black hole growth. She told Nature Journal, "These observations are pushing our models to their absolute breaking point. We might be missing something fundamental." Zoom out from individual galaxies and you see the universe's large-scale structure. Galaxies aren't randomly scattered. They cluster together in groups, which form galaxy clusters, which connect via filaments of dark matter and gas spanning hundreds of millions of light years. This cosmic web took billions of years to form, pulled together by gravity's patient hand. Or so we thought. Webb found the web already forming in the early universe. Vast structures, galaxy clusters, proto-superclusters, existing far earlier than models predicted. In 2023, astronomers announced the discovery of Sears 2112, a barred spiral galaxy existing 2 billion years after the Big Bang. Barred spirals are supposed to be mature, evolved galaxies. Finding one this early is like finding a grey-haired grandfather in a nursery. Barred spirals form when a galaxy's disk becomes gravitationally unstable, and stars arrange into elegant spiral arms with a central bar structure. This requires time, lots of orbits, gravitational interactions, a settled disk of stars. It's a late-stage development. Sears 2112 shouldn't exist. Yet there it is, perfectly formed, mocking our timelines. Then Webb spotted the Sparkler, a galaxy with dozens of globular clusters, dense balls of ancient stars. These clusters are usually found in old, mature galaxies. But the Sparkler exists in the early universe, already decorated with these stellar ornaments. More findings poured in. dusty galaxies in the early universe, even though dust comes from dead stars and shouldn't exist yet. Galaxies with chemical compositions indicating multiple generations of star formation and death, compressed into impossibly short timescales. It's like the universe had a cheat code. Someone pressed fast forward on galaxy evolution. Processes that should take 5 billion years happened in 500 million. Dr. Catherine Whitaker at the University of Massachusetts analyzed early massive galaxies and said, "We're seeing galaxies that look like they aged 10 billion years in just 1 billion years. That's not a rounding error. That's a completely different physics." So what's going on? Is the James Webb Space Telescope breaking cosmology? Or is cosmology just more complicated than we realized? Let's look at the possible explanations, from least to most radical. We measure cosmic distances using redshift, how much light has been stretched by the universe's expansion. It's a reliable technique, but early galaxies are faint and hard to analyze. Maybe some of these impossible galaxies are actually closer than we think, just masquerading as ultra-distant objects. Some astronomers checked. They took follow-up observations with better data. Most of the distances held up. A few galaxies were mismeasured and turned out younger, but many remained stubbornly ancient and massive. So the measurements are mostly correct, which means the problem is real. Maybe our models of star formation are incomplete. Perhaps in the early universe, conditions were so different that stars formed far more efficiently than they do today. The gas was denser, pristine, unburdened by heavy elements. Maybe that allowed rapid bursts of star formation we've never witnessed in the modern universe. This is plausible. It requires tweaking our models, but doesn't break fundamental physics. Many astronomers lean toward this explanation because it's the least disruptive. But here's the catch. Even optimistic star formation models can't fully account for what Webb's seeing. You can push the efficiency higher, but there are hard limits imposed by physics. Gas can only collapse so fast. Stars can only form so quickly. Even with perfect conditions, you run into bottlenecks. Then there's dark matter, the invisible stuff that makes up 85% of the universe's matter. We know it exists because we see its gravitational effects, but we don't know what it is. Maybe dark matter behaves differently in the early universe. Maybe it clumped together faster, creating deeper gravitational wells that accelerated galaxy formation. Some physicists propose warm dark matter or self-interacting dark matter with properties that could speed up structure formation. These models are speculative but gaining attention as Webb's discoveries pile up. Or maybe we're missing something about the Big Bang itself. The Lambda CDM model, our standard cosmology, might need revision. Perhaps the early universe expanded differently than we think. Perhaps there were additional phases of inflation. Perhaps fundamental constants weren't quite constant in the universe's first moments. This is where things get uncomfortable for scientists because you're not just tweaking models anymore. You're questioning the foundation. Some fringe theorists have gone further, suggesting tired light theories, or even that the Big Bang didn't happen. But these alternatives create more problems than they solve and contradict mountains of other evidence. The cosmic microwave background radiation, the abundance of light elements, the expansion rate, all of this fits the Big Bang model beautifully. Webb's discoveries are puzzling, not invalidating. The most likely answer: we're missing pieces of a complex puzzle. Galaxy formation in the early universe probably involves multiple factors we haven't fully understood. More efficient star formation, different dark matter behavior, unique conditions that don't exist in the modern cosmos, and processes we haven't imagined yet. Science isn't broken. It's doing what it's supposed to do, being challenged, tested, forced to evolve. Here's what makes this exciting rather than terrifying. We built a telescope that could actually challenge our understanding. That's extraordinary. Imagine if Webb looked out and confirmed everything exactly as predicted. That would be boring, safe, unchallenging. Instead, we're living through one of those rare moments in science when observations force us to reconsider fundamental assumptions. This happened when Edwin Hubble discovered the universe was expanding. It happened when Vera Rubin found evidence of dark matter. It happened when Perlmutter Schmidt and Riss discovered dark energy. Each time, astronomers thought they understood the universe. Each time, better observations revealed deeper mysteries. Webb is doing it again, and we're watching in real time as cosmology grapples with uncomfortable truths. The coming years will be fascinating. More observations are being made right now. Astronomers are refining their models, running new simulations, proposing bold theories. Some will be wrong, some will be partially right. Maybe one will be revolutionary. What we're witnessing is the scientific method at its finest. A telescope reveals something unexpected. Scientists question their assumptions. New hypotheses emerge. More observations test those hypotheses. Knowledge advances, even if slowly and painfully. The universe doesn't care about our theories. It simply exists, following rules we're still learning. And every time we think we've figured it out, it shows us something that makes us say, wait, how is that possible? That's not a flaw. That's the beauty of exploration. If we already knew everything, why would we look? The James Webb Space Telescope looked deeper into space than any instrument in human history. It saw further back in time than we've ever witnessed. And what it found challenges everything we thought we knew about how the universe began. Massive galaxies forming impossibly fast. Black holes growing beyond speed limits. Structures appearing before they should. The early universe was far more complex, far more active, far stranger than our models predicted. We don't have all the answers yet. We might not for years, maybe decades. But that's okay, because the questions we're asking now are better questions than the ones we asked before. And somewhere out there, in the deepest darkness that Webb can see, are secrets we haven't even begun to uncover. What do you think? Are we on the verge of rewriting cosmology, or will these mysteries fold neatly back into our understanding? Drop your thoughts in the comments. And if you want more deep dives into the universe's biggest mysteries, subscribe. Because Webb's only getting started, and trust me, things are about to get even stranger.